come back to the second half of today's lecture. So, what we did was we had commutative ring A, and to this commutative ring we have associated a topological space X, which is spectrum of A. So, first of all, what are the closed sets we have described? Now, let us describe the open sets. So, open subsets in X are precisely complements of the closed sets. In X, and we know what are the closed sets. So, open sets, they are the complement. So, that is X minus V of an ideal A. So, where A is an ideal in A, and this we denote it by D of A. So, how do you check that all right. So, these are the open sets. All right. Now, I want to check the functorial properties. So, that is, so let us describe it for a single element. What is D of F? So, if F is in A, what is D of F? D of F means D of ideal generated by F, but this means a complement of single equation F V F, but this is what? These are all those points X in X such that F is, X is not here means f x is non-zero. So, f x is non-zero. So, this is a open set. And similarly for finitely many equations, if Noetherian, then any open set. So, if A Noetherian, then any open set will look like D of F1 to Fm, which is the complement of x minus V of F1 to Fm. But this complement is same thing as, now you see this x minus, this is the intersection of V of Fi, Fj, j is from 1 to m. But the complement intersection De Morgan's law, that will become union D of Fj, j is from 1 to m. So, any open set, if A is Noetherian, then any open set will look like union of this basic open. These are called basic open sets. This DF is called a basic open set. Sets in X, and this always we consider with the Zariski topology. That topological space. All right. So, we know what are the open sets. All right. Now, I want to check the functorial properties. So, what does that mean? That means here I have category of rings, category of commutative rings. And with one, with unity. This is very important. So, to each ring we have associated a topological space. So, here is the category of topological spaces. So, category means, let me recall once, category means objects and morphisms. Objects here are commutative rings and morphisms are precisely the ring homomorphisms. And let me insist, ring homomorphisms carries 1 to 1. This we have seen is very important when we did localization and other things also. And this category is category of topological spaces, and morphisms are the continuous maps between the topological spaces. So now I am trying to define functor. Functor is what? Functor should be an association. For each object we associate an object here. So this we have associated already spec A. This is with the Zariski topology. We know that this is a topological space. We know it is open sets, we know closed sets, we know basic open sets also. Now our problem is when we have a ring homomorphism from A to B, phi, ring homomorphism. Then we want to associate so this B is associated to B we have associated this topological space. Now this was one of the main difficulty for classical geometry, classical algebraic geometry, that even if we have a finite type algebras over a field, we could not have associated the map on the maximal ideals, because the main difficulty was contraction of a maximal ideal is not maximal ideal if A or B is not a finite type algebra over a field. So that was one of the main difficulty. So now that difficulty is solved very easily, because we do have a map here, very easy map, that is phi star. And what is the map phi star? If you have any prime ideal, now it is also very neat to denote the elements x here and px here, that is earlier Grothendieck's notation, here y here and py here. Now it is clear from the notation that if I take any y, so that is py. So I will write both. So y, what do we do? How do we define phi star of y? This means phi inverse of the ideal py. See, py is a prime ideal here, and I just pull it back under phi, that is phi inverse of py. And we know this is indeed a prime ideal in A. Contraction of a prime ideal is a prime ideal, that we have checked several times. So therefore this makes sense. So the definition of phi star is, so phi star from y to x is defined by phi star of y equal to phi inverse of py. This is a prime ideal, so we call it px, and that is that x. So y going to x, where this x corresponds to phi inverse of py, and this corresponds means this is px. So this is that map. And now to show it is functorial, that means we have to show first of all that this is a continuous map, and if phi is identity, this is identity, and it respects the composition. So let us first show that it is continuous. So that is the next proposition. So proposition, let phi from A to B be a ring homomorphism then the map phi star from spec A, spec B, which is y, to x, which is spec A, defined by phi star of y equal to phi inverse of py, which is px, which is x, is continuous with respect to Zariski topologies on x and y respectively. So, we have to check that inverse image of a closed set is a closed set, or inverse image of a open set is open set. All right. So, in fact, so proof it is enough to check that for a subset E of A, we have phi star inverse of V of E equal to V of phi of E, and phi star inverse of D of E equal to D of phi of E. Because every closed set will look like V of some subset E. Every ideal, in fact you can take E to be ideal, and then this is a arbitrary closed set, and the inverse image of that is this one. So, here I prefer to write this because there is no ideal involved, it is only the sets are involved, and that is enough, because this actually will mean that if you take ideal E is ideal A, then you have to take the extended ideal, and that is generated by the image of the generating set for the ideal. So, therefore, these are enough, and this is not much complication. So, I will prove this, and I will prove this equality. This will follow from that, because you take the complements. So, we will prove the first equality. So, we are proving this. So, this is 1 and this is 2. So, 2 follows from 1, that is very clear. Now, proof of 1. All right. So, what do we do? I take a element here. See, where are the sets? Both the sets are in, this is V of phi of E. Phi of E is in B. So, V of that will be in Y. So, both these are subsets of Y. Both these are subsets of Y. So, I will start with any Y in Y, and I will say Y belongs here if and only if it belongs here. If and only if, that is why I want to check. So, the proof will become 2 line only. So, Y belong to this side, that is Y belong to phi star inverse of V of E means what? That is if and only if, that means phi star of Y belong to V. This means phi star of Y belongs to V of E. This is only set theory, there is nothing in that. And when do phi star Y belong to V of E? That is if and only if this is a prime ideal. Phi star Y is which prime ideal? That is this x, Px. So, this is a prime ideal, and when do that belong to V of E? That means every element of V of E should vanish here. So, that means vanish means it is contained here. So, this is if and only if E is contained in phi star of Y, which we know what it is, which is phi inverse of Py, which is x. But when is this? So if this, if E is contained this, again set theory, apply phi on both sides. So that is if and only if phi of E is contained in Py. But this subset is contained in Py. So the all elements of this subset will vanish at Y. So that is if and only if Y will belong to V of phi of E. Finish. So what made the difference in the proof is the notation due to Grothendieck. Alright, so we have proved that this map is continuous, and now also we will have to, for functoriality, we will have to check two more trivial conditions. I already said that. So for functorial properties are the following: functorial properties, that is, if phi equal to identity on the ring A, then phi star should also be identity on X, where X is spec A. That is one. And two is, if I have two ring homomorphism from A to B, phi, and B to C psi, then we have to check then composition, psi compose phi, and then the star is same thing as, now what? Now the arrows will change. So this will be phi star compose C star. You see this order has changed. That is because you see phi star is from spec B to spec A, that is phi star, and then spec C to spec B is C star. So first we are applying this and then this, you see. So it is a contravariant functor. So this, what we have proved is the functor is contravariant. From category of rings, so that I will denote rings like this, category of rings, commutative rings. So maybe you write C here, to the category of topological spaces, tops. This is the functor we have defined, A going to spec A. Now also we also have to come back, then only it becomes a good association. So that means we want to define a functor from the other direction, so that there is a two-way traffic, and when we do that, then only the real abstract algebraic geometry will start. So right now we are going from category of rings to category of topological spaces, and we are collecting information about the properties, etc., etc. Alright, so this we will do it. I do not know whether I will be able to do it in this course to go back, because that will involve more machinery, especially from the topological side, what is called a sheaf theory. I am not going to, that will be beyond this course. So we will not do that, but we will only understand this association better and better. And I want to give you some examples where this association helps. Alright, so first couple of notes I want to make, which I have not checked in this abstract sense. So first of all, V of A is equal to V of radical of A. That is obvious, because what was V of A? V of A is by definition, I will write geometric. So x in x such that f of x is 0 for all f in A. This was V of A, and which containment is obvious? The smaller the ideal, bigger the V. So this is clear. This is clear. Now conversely, if suppose somebody is somebody is not here, then it will not be here. That is what I will check. Somebody not here means what? That means there is a f. So, x not in V of root A means there exists. So, this means that is there exists at least one element in root ideal which does not vanish on x. So, there exists G in the root of A such that with G of x is non-zero, but the G is in the radical means some power of G, G power R belongs to A. This is non-zero, G power R. But what is G power Rx? G power Rx is, as I said, evaluation is a ring homomorphism. This is therefore Gx power R, and if Gx is non-zero element in the field, the power of that is also 0. So, this is also non-zero. So, since kappa x is a field, but this is same thing as, so this is, so we found an element in the ideal which does not vanish at this given x. So, therefore, this proves that this implies that x does not belong to V of A. So, therefore, they are equal. So, that proves the equality here. So, as in the earlier classical case, V does not depend on the, V depends only on the radical ideal. So, think of V as a map from the radical ideals in the ring A. This was the notation I introduced earlier, to where? To close subsets in X, where X is spec A, and obviously with Zariski topology. And as I said, I want to come back. So, at least I want to define a map, that I map, no, that was IK map in that case. So, I want to define a map in this direction. So, we want to define this. So, what is the map? Take any and I will define it for actually for arbitrary subset y of Px, y of x. If y is a subset of, that means I am defining a map from the power set of x. So, take any subset y of x, I want to define a radical ideal there. And what is that? As I said, you imitate. So, y map it to where? Iy, I of y, then this should be by definition what? Intersection running over y in y, Py. This makes sense. And obviously, this is a radical ideal, because each prime ideal is a radical ideal and intersection of a radical ideal is a radical ideal. So, here since each Py is a radical ideal, and intersection of radical ideals is again a radical ideal. So, we have defined the map in the both ways. Now, what obvious? Now, we want to check that at least one composition, what would you like that the Null-Stensatz, for example, what will be that? What was the Null-Stensatz in a classical case? When you take a closed set, you apply the ideal and then apply, or you take a closed set, apply the ideal, then what do you get? You get the radical of that ideal. This is classical. So, what was the classical? Let us recall classical Null-Stensatz was, this was classical. I will recall this HNS. This was HNS2 if you remember our notation. What was that? Ik of Vk of an ideal A, where A is a radical ideal or arbitrary ideal, then you have to write the root ideal here. This was the classical. So what will be the corresponding there? So that I will call a formal Null-Standards. And you will see this proof will be obvious, formal HNS. What should it be? For every ideal A in the ring A, we have what equality? I of V of A equal to radical of A. This is what we want to prove. And what is obvious? Let us write down first definition. So to prove this, to prove this, obviously we will replace this A by the radical ideal, and then we may assume that A equal to root A. Because if you change this to root A, this V will not change, and this will get changed to root of root A, which is A. So we can assume this. Now let us check both sides. What is the other side? A is a radical ideal we are assuming now. So what is A? So since A is a radical ideal in A, we know A is precisely the intersection of all P where A contains P. This we know because this is precisely. So to check this, you go mod, pass on from A to A mod A. Then what do you have to check? This A will become 0, and then this becomes a nil radical. So therefore not 0. So this will, when you pass on from here to here, we need to check that the radical of 0 ideal equal to precisely the intersection of all prime ideals. But that we know. We have checked the nil radical is precisely the intersection of prime ideal. So this we know it from there. Just pass on to this ring and check. Alright. So what is the other side? Okay. So what is V of, so this is also, I will rewrite this. This is intersection of all P x, so that x belongs to V of A. I just rewrote it. What is the other side? So this is what is I of V of A. This is by definition, this is my y. So this is intersection y in, not y, let me call it x only, because there is no other ring V. X in V of A such that this is Px. But that is precisely this. So it needs nothing. It only as easy as to check that the nil radical in a ring is precisely the intersection of all prime ideals. So the Null-Standards became trivial. So that is another gain. So abstract, so this is precisely the abstract. So I will just mention here abstract algebraic geometry. This is precisely the study of the maps V and I. V from ideal radical ideals of the ring A to the closed subsets in spec A, and the other way. So, I is the other way map, this way map, this way map. I should write it I here. So, that is namely any subset, in fact it is defined for any subset y is defined to be y to I of y, and I of y is by definition intersection py as y varies in y. So, this will give, and we want to keep studying these correspondences, and for example we would like to know when can you recover back your ring from this topological space, and this data will not be enough. So, we will have to go down to more structure, we will have to look for more structure on spec A. Right now we only know it as a topological space. So, we need to know more structures on the spectrum to recover the ring A, and that will become real abstract algebraic geometry, and in this case this more structure that we cannot do, this is called a shift A. This is precisely the scheme structure. So, that we will not do. So, that language is developed by the Grothendieck or in 50s and 60s, and that is usually called language of schemes. So, if you see the algebraic geometry books, normally they will start with schemes, affine schemes and so on and so on. So, I will not get into this course on the abstract structure, but on the other hand I will study these correspondences V and I more closely. For example, when can you given a ring homomorphism, we know when the map we have defined a continuous map. Now, one can ask a question, when can that map be a closed map, and so on. When can it be open map, when can it be closed map, when can it be homeomorphism, and such questions. So, and then in the next time I will give you some more examples of this association. For example, what are the close points, what are the irreducible subsets, what are the irreducible components. This I will do it in the next lecture, and then the course will come to end, but it will show up how important is the commutative algebra in this course. Thank you very much. We will continue in the next lecture.